Thank you for joining me again. Here is another section, and in this section, we want to solve some examples on the formation of differential equations. And I promise you it's going to be engaging and interactive. So follow me. Form differential equations by differentiating and eliminating the constants a and b from the following functions. And in the last class, I explained to you that you have to note the constant. How many constants are present in the given function? Because the number of these constants determine how many times you are going to differentiate the given function. So in the first one, A, we have y equals ax plus b. So we can say that we have how many parameters, which are the constants. The parameters are A and B. So the parameters, that is the constants, are A and B. So that means we have two parameters, two constants. We have two constants. So since we have two constants, that means we are differentiating twice. So we are differentiating twice. So let's go on with the first differentiation. So differentiate y. So we have to be 1 then multiplied by the y the x. So we have the y the x equals ax. If you differentiate this one, it's going to give us a. So let's call this one equation 1. So we are differentiating twice. Remember, so let's differentiate again. So we have d squared y, the x squared equals 0. So from the previous class, we said that the remaining differential equation after the elimination of constants is our required differential equation. So that means our required differential equation for this function y equals ax plus b is what? The squared y, the x squared is equal to 0. So, and we can write it as y prime prime is equal to 0. So that is our required differential equation. B, y equals ax. We have just a constant, one constant. So since we have one constant, which is a, so we are differentiating once. So let's differentiate once. So differentiating y with respect to x gives 1 divided by x. So it will be dy dx. Differentiating ax gives what? A. So this is equation 1 and here is equation 2. So from equation 2, our a is equal to dy dx. So let's substitute equation 2 into equation 1. So anywhere I see a in equation 1, I'll put what? Dy dx. So because I want to eliminate the constants. So y equals dy dx, then multiply by what? X. So recall dy dx can also be written as what? Y prime. So we can say that, recall. So our y equals what? Y prime multiplied by x. So it can be written as y divided by x equals y prime. So we can write it as y prime equals y over x. So you can write it anyhow that is convenient for you. So, but this is our the required differential equation. So C R equals A cos theta. So here also it's just a constant, so that means we are differentiating once. So let's differentiate r with respect to theta, because theta here is our independent variable. So this is the dependent variable, and here is the only constant that we have. So this one will give us the r d theta equals the constant. Then if you differentiate cos theta, is going to give us what? Minus sine theta. So that means the r the theta equals what? Minus a sine theta. So call this one equation 2, call this one equation 1. So from equation 1, we want to eliminate the constant a now. From equation 1, let's make A the subject of the formula. A is equal to r divided by cos theta. So this is equation 3. So substituting equation 3 into equation 2 gives, that means anywhere I see A, I'm putting what's there? R divided by cos theta. So here I have minus A, I put R over cos theta, then multiply by sine theta. So the r d theta equals minus r, then multiply by 1 over cos theta, multiply by what? Sine theta. So we have the r d theta equals minus r multiplied by sine theta over cos theta. And if you could remember that tan theta equals what? Sine theta over cos theta. So we are going to substitute this. So the r the theta equals minus r tan theta, and here is our required differential equation since there are no more constants there. So that is for C. So for D, D x, y equals A. We have one constant which is what? A. So differentiate once. So if you differentiate this one implicitly, so that means we are going to differentiate it using product rule. So differentiate x, then leave y, will give us y. That is x, differentiating x with respect to y is 1. Then you leave y. Plus leave x, differentiate y, will give us the y dx equals 0. So this is our required differential equation. Since there are no more constant, there is no more constant because we have just one constant. So this is the required differential equation. E, y equals a exponential x. So here we have just a constant. We are going to differentiate it once. So we have the y dx equals what? A exponential x. So from here, from equation 1, let's make A the subject. So it will be y over exponential x. So let's substitute this into equation 2. This is equation 1, this is equation 2, and here is equation 3. So substituting equation 3 into equation 2 gives the y dx equals, anywhere I see here I'm putting y over exponential x, then multiply by exponential x. So exponential x cancel exponential x. So I have the y dx equals y, and that is my required differential equation. required differential equation. F is equal to exponential bx, so we have just one constant, so that means we are differentiating once. But please, you have to understand this. We have to find way of eliminating the exponential. So what do? You take logarithm of both sides. So ln, so natural logarithm of both sides. So ln y equals ln of exponential bx. So the ln will cancel the exponential. So we have ln y equals bx. You can see we have simplified it now. So from here, we are going to differentiate now, just once. So differentiating ln y gives us 1 over y, then dy dx equals differentiate bx gives b. So from here, if we cross multiply, we have dy okay, let's leave it like this. Let's leave it like this. So this is our equation 1 and here is our equation 2. So anywhere we see b, we are putting what? 1 over y dy dx. So ln y equals 1 over y dy dx multiplied by x. So you can leave it like this, or you cross multiply. We have ln y equals x over y dy dx. So we have y ln y equals x dy dx. So we can also say that dy dx equals y over x ln y, and that is our required differential equation. So I wanted to understand it. I still have more for you. So in the next video, I'm going to solve another examples. Thank you. Bye bye.